Hello friends, in this video we'll see the topic Cauchy sequences of real numbers. Let's see definition of Cauchy sequence. A sequence xn of real numbers is said to be Cauchy sequence if for any given epsilon greater than 0, for any given epsilon greater than 0, there exists a natural number n naught such that mod of xn minus xn means difference between xn and xm means xn is nothing but nth term of the sequence xn and xm means mth term of the sequence xn. This difference is less than epsilon for all n greater equal n and m greater equal n naught. Means the difference between terms is decreasing, right? Then we have to call that sequence xn of real numbers a Cauchy sequence. See, for example, let xn is equal to 1 by n for n belongs to n. Then the sequence xn of real numbers is a Cauchy sequence. Is a Cauchy sequence. See, you can observe that 0, 1. The first term sequence 1 by n is 1, second term is 1 by 2, third term is 1 by 3, next term is 1 by 4, next term is 1 by 5, next term is 1 by 6, 1 by 7, and so on. You can see that the terms of the sequence means difference between terms of the sequence is decreasing here, right? Therefore, sequence 1 by n is a Cauchy sequence. Okay. There is a relation between Cauchy sequence and convergence sequence of real numbers. Let's see. Every convergent sequence of real numbers is a Cauchy sequence. Every convergent sequence of real numbers is a Cauchy sequence. Okay. Let's see the proof. Means if you take any convergent sequence of real numbers, it satisfies the definition of Cauchy sequence. Okay. Let xn be any convergent sequence of real numbers. We claim that xn is a Cauchy sequence. Okay. Let epsilon greater than 0 be any given positive real number. See, we have xn is a Cauchy is a convergence sequence. Therefore, there exists a real number L such that a sequence xn converges to L, and therefore, since epsilon is positive, epsilon by 2 is also positive. Therefore, for epsilon by 2 greater than 0, there exists a natural number n naught such that the difference between xn and L is less than epsilon by 2 for all n greater equal n naught. This is because xn is a convergent sequence of real numbers. Okay. Consider mod of xn and xn. We can write it as mod of xn minus L plus L or minus xm plus L. Okay. And see, we have added and subtracted L, so to keep its value remain same. And see, this is true for all n and m belongs to a set of natural number, right? Okay. We can write this term as xn minus L plus minus xm plus L. This is also true for any natural number n and m. By triangle inequality, we can write right side as xn minus L less than or equal to xn minus L plus minus xm plus L. Means mod of xn minus xm is less than or equal to this term. But we know that mod of minus a is equal to mod of a for any real number a. So we can write this second term as mod of xm minus L, and this is true for any natural numbers n and m. Okay. Call this as 1. Now, if we take n and m greater equal n naught, then if n is greater than n naught, then mod of xn minus L is less than epsilon by 2, and if m is greater equal n naught, xm minus L is also less than epsilon by 2. So it implies the addition of left hand sides of these two terms is less than or is strictly less than addition of right hand sides. Okay. But from 1, the term which is in left hand side, which is less than or which is greater equal mod of xm minus xn minus xm. Therefore, we can write what, mod of xn minus xm is strictly less than epsilon by 2 plus epsilon by 2, that is less than epsilon. Means we proved that for any given epsilon greater than 0, there exists a natural number n naught. This natural number, there exists a natural number n naught such that mod of xn minus xm is less than epsilon for all n and m greater equal n naught, and hence we proved that xn is a Cauchy sequence. Okay, this is the end of the proof. Means we proved that by taking any convergence sequence of real numbers, we proved that it is a Cauchy sequence, and hence every convergence sequence of real numbers is a Cauchy sequence. Note that every Cauchy sequence of real numbers is also a convergence sequence. Means the statement, the theorem we proved, its converse is also true for sequences of real numbers. Means every Cauchy sequence of real numbers, means xn is a Cauchy sequence of real numbers, then it is convergent sequence, right? And since every Cauchy sequence of real numbers is convergent sequence, and we know that every convergent sequence of real numbers is a bounded sequence. By combining these two statements, we can say that every Cauchy sequence of real numbers is convergent by note 1, and every convergent sequence of real numbers is bounded. So we can say that every Cauchy sequence of real numbers is bounded sequence. Okay. Now I'm stopping the video. Thanks for watching.